request. And it's covering chapter 3 and then some, right? Because we said by popular demand the asymptotes, the limits have to be there due to the abysmal performance on the first exam in that area. So first we are covering chapter 3 plus 2.4/2.5. Those are the sections for vertical and horizontal asymptotes, and we're going to talk about that. So let's start there. 2.4 vertical asymptote, limit x goes to a value c, either plus or minus, of the function f of x is going to give us positive or negative infinity, implies VA at x equals c. So you either approach from the left or right and you get one of the infinities. So that was the definition for vertical asymptote, and you were supposed to do that limit to prove that there is the vertical asymptote at given x value. 2.5 is the horizontal asymptote, also featured on the exam. I put the stream up? Yep. Okay, good. Which is limit x goes to either positive or negative infinity of the function is going to give us some finite value L. If that is true, then we have the horizontal asymptote at y equals L. So these two definitions are calculus definitions for asymptotes, and you apply the limit to the function you get at the point or at infinity, and you will see whether there is or there is not an asymptote there. You still have to set denominator equal to 0 for vertical asymptote to find all the candidates for the asymptote, and then you have to run the limit to see which one of those, one or both or none, or I don't know how many you find, are asymptotes or not asymptotes. So that's the part from the previous chapter that will definitely be on the exam showing up. Then we're going into chapter 3. We have limit definition, one question of the derivative, which means you will be computing one of those f prime of x is equal to limit h goes to 0 of f of x plus h minus f of x divided by h. So that's one question. And then we have basic derivatives. So probably a question with all of the what's the derivative of x squared, what's the derivative of cosine x, what's the derivative of inverse tangent x. We said you have to know that one. So a basic one. Then we have product, quotient, chain, rules. We have implicit. There are two sections that are talking about trigonometric derivatives. There is a logarithmic differentiation. And the most important thing is that for all of these here, all of them, I'm not going to exaggerate, so I'm just going to write it this way, tangent. Oh, I can't fit. Ah. All right. Tangent line problem. So tangent line problem, we know that you you first find the derivative, then you plug x value to find the slope. Step 1, find the derivative. You find the derivative by any of these ways. So the tangent line problem could have any of these as the input, and then you just plug in the values to find the slope. So tangent line problem spans over the whole range. And we have word problems, and we're done. So related rates. So that's it on the exam. So chapter 3 is mainly learning the basic rules of differentiation. Basic rules of differentiation in terms of, I don't know, x squared, x cubed, and so on. Yes? Of the two that I mentioned, yes, the inverse sine and inverse tangent, yes. The other ones, if they show up, it will be given. So inverse cos secant, I mean, people don't usually memorize those. There are not that many formulas that you are learning / memorizing here. If you didn't know any of the limit ones for asymptotes, obviously, there are 2 over there. Then you have the limit definition, that's 3. Product, quotient, chain rule. Implicit differentiation is a procedure, it's not a formula. Trigonometric derivatives, derivative of sine and cosine, that all falls under basic stuff, so not. Logarithmic differentiation is also a procedure. So we're talking about 6 formulas, and then basic derivatives. And related rates, as again, it's a procedure. If you're able to find to understand from the text what is your geometry that you should draw and what equation you should write, the rest is just take the derivative in respect to t and plug the numbers in. So every problem is solved the same way, except when it gets really ugly with equations. Technically, that's it. Fair? Good. At this point, because my part of review is done, right? At this point, let's open the floor for questions. Do you have any questions, or we're done? Yes.
Can you do number 36 on 3.1 exercise?
36? Let's see if I can. So what are we supposed to do? Use the definition to find the limit, to find the derivative? Is that true?
Yeah.
3.1, problem 36. Function f of x is given to us as 1 over 3x minus 1. A equals to 1, that smells like a tangent line.
You know,
Oh yeah, awesome. All right. So what are we going to do here? First of all, they're asking us to find the tangent line using the limit method. So let's do that. Limit h goes to 0, f of x plus h, which is 1 over 3 open parenthesis x plus h close parenthesis minus 1, minus 1 over 3x minus 1 divided by h. The only thing we can do is cross multiply, do the common denominator to subtract the numerator. Denominator stays as h. So what do I have upstairs? I have 3x minus 1 minus 3x plus 3h plus 1. You have to change the signs because there is a negative, right? Divided by, open parenthesis, 3x plus h minus 1 times 3x minus 1. So now you see that in the numerator, all of these guys cancel, leaving only 3h. So what do we have? We have the limit, age goes to 0, and I'm going to deal with a double fraction now, which means that I can put age over 1. That's a common trick, right? So now two that are far apart multiply on top, so that's going to be just 3age. And two that are close by multiply on the bottom, which means age times the whole mess of 3x plus age minus 1 times 3x minus 1. So that's some algebra there. You see that the age cancels. And at this point, we can actually plug in age is equal to 0. Because the age that was making denominator 0 disappeared, now we can just plug in. Becomes an easy problem. So it's now 3 divided by, and this age is gone, so it's 3x minus 1 times 3x minus 1. So just going to put the square there. And that's the derivative.
So then you would plug in 8 for x.
Yep. Very good. So now the slope is when you take the derivative and compute at value a, which is the derivative in our case computed at 1, which is 3 over 3 times 1 minus 1 squared, which is 3 over 4, right, when you compute. So we get 3/4. So what do I have now? I have slope, which is m is 3/4, and I also have a, 1. I need to find f of a because that's going to be my y. This is my x, and this is going to be my y. So how much is f of a? F of a is f of 1, which is plugging in the original equation. We get 1 over 2, 1/2. Let me write it. 1 over 3 times 1 minus 1, which is 1/2.
So realistically, you can find that before you even take the derivative, right?
Yes. You can find the y value. If it's not given to you, you can find the y value before you take the derivative. Sure.
So it makes more sense to do that.
Whatever makes you happy. This is calculus class. It's important for all students to be happy at all time. It's a calculus class. So if that makes you happy, compute the y value first and then go with the derivative. I see a few smiles, at least 3, which is awesome. In a classroom of 12, great. So now we are going to do 1/2 is equal to 3/4 times x is 1 plus b. And this is where we calculate b. So b is 1/2 minus 3/4, which is negative 1/4. So the tangent line is y equals 3/4 x minus 1/4. Procedure for the tangent line is always the same. We first find the derivative, well, first find the y value, if it's not given, all right, because that makes you happy. And then we find the derivative, plug in x value into derivative to find slope m, and then you have mx and y, and then find the line. The only time when you have to be a little bit careful is if the derivative is for the implicit, because the implicit one is going to give you on the other end x's and y's when you find the derivative moves together. In that case, you have to plug in x and y, and every dy dx will be m. So that's the only one that is oddball in terms of calculating the slope. And you still find the derivative, except it's implicit, so it looks a little bit weird. But in that case, you will have both x and y given, and you plug both of them in, and you figure it out. Counter slope. Anything else? Any other questions?
You're gonna have problems with like marginal cost and all that stuff, acceleration, velocity.
Is that a request or a question?
I don't. No, it's a non-request.
Non-request. All right. The chances are no, but if I run out of stuff, maybe even replacement, you know. Because application of the derivative. I mean, you have the equation given. You will not be ever asked. See, that one should be your favorite pick over the related rates, because for related rates, you have to come up with the equation and then differentiate and do the rest. Where for this one, equation is always given to you. You just need to differentiate and compute. So those problems are always much, much cheaper than the related rates one, right? But we have to have related rates because that is the learning outcome of the course. Plus my favorite stuff. I mean, come on. Where would I be without tangent line and that? Yes?
It said find the inverse function and then the derivative, and the function was f of x equals the square root of x plus 18.
It said the inverse function
Yeah.
Using the derivative?
Inverse function, yeah, and then find the derivative. And it was square root of x plus 18 for when x is greater than or equal to negative 18.
All right, so, but the function is given. F of x is what?
Square root of x plus 18.
X plus 18, like this.
Yeah.
All right, and they're asking for the derivative.
The inverse function and then the derivative.
Uh-huh. All right.
For when x is greater than or equal to negative 18.
Okay, so we are going to find the inverse, the inverse function first, and then later the derivative of the inverse function. So step 1 and then step 2. All right. So we start by writing y equals square root of x plus 18. We are going to square both sides to get rid of the square root. Sorry, interchange x and y first. And then solve, so it's x squared is equal to y plus 18. So here's our inverse function. I don't know why I do this. So inverse function is given as x squared minus 18. And now we find the inverse. We find the derivative. So the derivative of the inverse function is going to be 2x.
So once we have the inverse function as x squared equals y plus 18, you just flip the x and the y's again?
I flip them only once to find the inverse, and that's it.
What happens to the y then? We have x squared equals y plus 18, and then the arrow.
Well, y is the f inverse, right? I'm just calling it. I'm just giving it a name, right? So I solve for y, and that is the inverse. So that particular function will undo whatever you put in the. So these two, this one and this one, are inverses of each other. So if you say x is equal to 7 in the first one, if you say x is equal to 7, 7 plus 18 is 25, square root of 25 is 5. If you plug in 5 over here, you're going to get 7 back. So 5 squared is 25, minus 18 is 7. That's where it started. Right? That's the purpose of the inverse, to retrieve the old input. All right, next question. Anyone else?
It would be second derivative problem.
Yeah, that falls into the derivative. You just don't want the nested chain rule in the product rule on the second derivative. That's the only thing you don't want. Yeah, there will be second derivative. Yes. I can't hear you. Implicit, you say implicit echelon? Yeah. Which one? I don't know. Just find one. You know how I roll. You'll find it, I do it. Tomorrow, I find it, you do it. I was false. a spicy problem incoming. Tangent line with the implicit derivative. Awesome. So the problem says x squared cosine squared y minus sine y is equal to 0, and the point is 0 pi for the tangent line, where the tangent line is supposed to intersect the function. So, as it always is, we first find the derivative. It's implicit derivative because the y's are buried within the equation, cannot be solved for y. We see the product rule starting right off the product rule and then following the chain rule in the same term. So we have to be careful about that. We have function x squared times the function cosine squared. So that's the product rule. Copy the first. Derivative of the second is going to be 2 cosine y times the derivative of cosine is negative sine. And because we took the derivative in respect to y, we follow with dy dx. Plus, we're still in product rule. Copy the second, which is cosine squared y, times the derivative of the first, which is 2x. Minus derivative of sine is cosine, so cosine y, again dy dx, equal to 0. Now here's the trick. You could go and spend about 15 hours solving this algebra to get dy dx equal everything else. But why? Just plug everything right there, replacing every dy dx with m, which is the slope you're looking for, and see what happens. So now, the entire first term is going to be 0 because this guy is 0, and they all multiply together. So that's done. This term is 0 immediately because, again, there is 0 right there. X is equal to 0. And for this one, I have is the only one that survives. This one is the only one that survives. So what do I have? I have a cosine of y, but y is pi. So I have negative cosine pi times m is equal to 0. How much is cosine of pi? Very good. So that means that we have 1 times m, so m is 0. Awesome. You don't have to solve for dy dx. You just plug everything in. And if one of these guys over here makes a 0, the whole term dies. So now we have the slope is 0. We have the point 0 pi. Y equal mx plus b. So pi is equal to slope of 0 times 0 plus b. B equals to pi. So y equals pi is a horizontal line. Zero slope means it's horizontal line, and it goes through pi as a value. We call this horizontal tangency. And yeah, that's it. We'll talk more about that right after the test. We're coming back to this concept of horizontal tangencies, and we'll talk about the relationship between the function derivative and min, max, all that cool stuff. Not now. So for implicit derivatives, we take the derivative, right, for the tangent lines, we take the derivative, we plug in x, plug in y, we compute. And you replace every dy dx with m. And you know, it simplifies much faster than if you were to try and solve algebra, leaving these two terms, moving that term, then factoring dy dx. It's just going to be line after line after line. Just plug in immediately. Plug in immediately a value x, value y, and you're done. That's how quickly these problems can be solved.
This one's kind of easy though with the zeros.
This was well, actually, this is the hardest one in the batch of. Okay, find another.
Yeah.
You are now in charge. Find another one.
Are we gonna have second derivatives of implicit?
Why do you want
I'm just wondering.
Why do you want
that? I see it on the homework.
Yeah. No, let's not go with the second. It's just the first one is annoying enough, and then the second one is. I mean, if I end up putting up there, it's just because I don't have it on my short term memory. Way too much to do that.
I will sit wrong.
Oh, really? What do I do with 500?
I mean, exactly. You could watch TV and be exercise and keep brainwashing. Look, this is healthy.
I never do it. X in a while. I just find it sometimes.
Speaking of the LNs and stuff like
This is problem 29 from 3.8. It says cosine of x minus y plus sine y equals to square root of 2. And the point is pi over 2, pi over 4. So, we start again with, well, how about you do this for about, do this for about 2 minutes. Find the implicit derivative and, yeah. Find the implicit derivative and see. All right, what?
I don't remember how to do it. I know. I have all of it's possible.
Ready. About now. Do the same thing we did with the numbers, right? I take the y plus the y. 1 and x and line m. Then plug in now x, y, and m, and then I'm gonna do this more often. That's exercise. Let's take a look at this problem together. So derivative of cosine is negative sine. We copy x minus y, and then in a chain we take the derivative of x minus y, which is 1 minus dy dx. Derivative of x in respect to x is 1. Derivative of y in respect to x is dy dx. Plus derivative of sine y is cosine y. Again, we were taking derivative of y, so dy dx. Equals to 0, derivative of a number, square root of 2. Now we plug in pi over 2 for every x and pi over 4 for every y, and replace all dy dx's with m's. So minus sine of pi over 2 minus pi over 4 times 1 minus m plus cosine of y, which is pi over 4, times m is equal to 0. We are solving for m. So sine of pi over 2 minus pi over 4 is pi over 4. So sine of pi over 4 is root 2 over 2. And then we have 1 minus m. Plus cosine of pi over 4 is also root 2 over 2 times m is equal to 0. Distribute minus root 2 over 2 plus root 2 over 2m plus root 2 over 2m is equal to 0. Move root 2 over 2 to the other side, and these two, when they add up together, you get root 2 over root 2m is equal to positive root 2 over 2. Multiply both sides by 1 over root 2. Root 2's actually cancel on both sides, and m works out to be a half. Awesome. We still have our pi over 2, pi over 4 point. So the tangent line is y is pi over 4 is equal to 1/2 of pi over 2 plus b. So pi over 4 is equal to pi over 4 plus b. So b is 0. So tangent line at y equal 1/2 x plus 0 for b, so just 1/2 x. Awesome problem. Yeah, no one is sleeping tonight, huh? Any other questions?
Can we do like the multiple chain rule?
Sure. Do you have anything in mind?
Yeah. 192.
Page 192.
About 48.
48. I was about to put this on the test. No, I'm just kidding. So the chain rule section, I believe that's 4.67? 3.7, right? 3.7. So 3.7, problem 48. So y is equal to sine squared. In parentheses, we have e to the 3x plus 1. So the first question is, how many functions do we have? Well, the one on the outer function is definitely x squared because it's sine squared. And then we go one function in, which is sine x. Then we go another function in, which is going to be e to the x. And all of the way on the bottom down there is 3x plus 1 as the most basic function. So just try to put this back in your head. So 3x plus 1 replaces this x, makes this piece. Then that thing plugs into here, makes your sine of that, and then everything is squared. Because this square, you can put parentheses around everything and put the square on the outside. So just decomposing it, now we see there are 4 functions there, which means that we are going to have a derivative and then 3 chains following. So the most outer, maybe if I rewrite it, let me rewrite it one more time so it's easier for you to see. I hope it's better now. So the square on a sine can be written on the outside like that with parentheses. So you see that the most outer function is x squared. And then you have the one step in is sine x, another step in is e to the x, another step in is the exponent of e to the x, which is 3x plus 1. So now, the most outer function is x squared, whose derivative is 2x, but x is all the guts there. So it's going to be, for the derivative, it's going to be 2 times sine e to the 3x plus 1. So that's like writing 2x. Then the derivative of the inside, but the derivative of the inside is sine, so the derivative of that is cosine, and then copy again that stuff. Then the derivative of the inside is going to be e to the 3x plus 1, and the derivative of the inside is going to be 3. So we have 1, 2, 3, 4. And now I'm going to actually just code them a little bit. This is like the derivative of e to the x, of x squared. This is the derivative of sine x. This is the derivative of e to the x. And this is the derivative of 3x plus 1. So the derivative of x squared is going to give us 2x, but x is all the mess. Derivative of sine, which was inside, which was old x, derivative of that is cosine, followed by the chain, the derivative of the inside again, which is e to the 3x plus 1, and then derivative of 3 of the exponent. And now you can actually just clean it up a little bit. Depends on how much math you know. I mean, this is pretty much done, but 2 sine cosine could all be just sine of the double angle. And then you are multiplying that by 3e to the 3x plus 1. So that's the most compressed version of the answer. So the blue one over here is saying that 2 sine x cosine x is equal to sine 2x. It's a basic identity from your trig course. Yes? I can't hear you. Again, well, see, it's not a big deal for this exam to compress it because we're not going to go with set it equal to 0 and find min and max. But then the test 3 is coming up eventually, within like 10 days, which is, this is technically required, right? Because, I mean, you can set this one to 0, and this one to 0, and this one to 0, or you can set this one to 0 and say this one is not going to give any zeros out of it because it's exponential. This one will. And then you just do that one equal to 0, which is one thing, rather than having 3 things over there. So factoring and condensing it helps us for the chapter 4. So if you do it now, that's great because you're getting ready for chapter 4. If you don't do it now, well, still no big deal. It's chapter 3. But chapter 4 is coming.
No, I All
right. Are there any other questions? We still have 3 minutes left and then another 30 after that. Yes?
Where's the book?
You can pick any.
Did he ask for related rates?
He said 3-6.
3-6 and related rates.
Oh.
You want to pick problem, just go for it.
Yes. Here's the related rates problem. We're going to take a look at a highway chase for related rates. Now this problem is not in your textbook, so I will have to really explain it. And then, you know, you can always go back and watch the stream recording and decipher. So a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that is turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour and the instant of measurement, what is the speed of the car? So I'm going to draw an intersection here. I'm going to put the cop car over here. The cop car will have the red and the blue light, as we are all familiar with that. Going into the intersection this way. The other car that is trying to run away, it's right here, will not have red, and it's going that way, and there was the radar in between them like this. So we know the distances because the cop is 0.6 miles this way, the car is 0.8 miles that way, and the distance between them is 20 miles per hour, and the cop car is moving this way at 60 miles per hour. That's 60 miles per hour. I know mph, but miles per hour as a fraction. All right. So now what I'm going to do is I'm actually going to draw a triangle that doesn't have any of these pretty drawings there. It's just a triangle. I should have drawn this one shorter, but just deal with that. All right, all adults here. So this is my x, and this is my y, and this is something that it's important, those reference points, so you guys can get the minuses and pluses straight. The y appears to be negative over here. So if y is negative, right, it's going, oh wait, the car is actually, did I say from the west or from the, our police cruiser is approaching a right angle intersection from the north. It's not going north, it's coming from the north, which means I have to now draw the whole thing again. The cop car is here. There we go. Now we're going to get rid of all of this stuff and draw 0.6. Well, that means that I have to redraw all of this stuff as well. 0.6, and then there's going to be distance of 20 miles per hour, and the car is going down 60 miles per hour. So that's all that. Now, the cop car is going down 0.6. This is 0.8, so a little bit longer, or much longer. We have 0.6, we have 0.8, we have 20 miles per hour, and we have also that this point here is moving down, and this is where I'm going to write negative 60 miles per hour. I'm writing negative 60 miles per hour because it's going down. We know that on the xy, this motion is positive, this motion is negative. So it's just from the reference point. Yes? Well, as you see at the end, the minus and plus signs only show in which direction you're moving. So that's it for physics, so the reference point. So it really doesn't matter. If you end up with a negative answer and it's negative 60, you know it's negative 60 the opposite way that you chose to be the direction. That's all it is. We have this to be our x, we have this to be our y, and this is going to be capital D, distance between two cars. We have x squared plus y squared is equal to the distance squared, separation. And we are looking to see how fast is this car moving, which is dx dt, right? Because it's on the x-axis, so it's speed. I mean, you can call it dc, right, for the car, but dx is fine. So now we are differentiating 2x dx dt plus 2y dy dt is equal to 2d dd dt. All 2's drop. We have x as 0.8. We are looking for this one. We have y, which is 0.6. We have dy dx, which is the speed, which is 60. We have the dd, which is 20. And the only thing that I don't have is d, but I can solve the Pythagorean theorem and find d from the Pythagorean theorem. So to get d, we have d squared is equal to 0.6 squared plus 0.8 squared, which is 0.36 plus 0.64, which is 1. So square root of 1 is 1, so d is 1. And 0.8 dx dt plus 36 is equal to 20. I'm sorry?
Are we making it 60 or negative?
Oh, yeah, minus. You're right, minus, because 60 is negative. I forgot to put the minus there. Yep. And all I have to do now is to add 36 to the other side. I get 56, and then 0.8 gives us 70. So dx dt 0.8. Well, you can write 0.8 as 4/5, right? Is equal to 56, and then times 5/4 times 5/4. So dx dt is equal to 4, and that's 114 times 5, which is 70 miles per hour. So if the cop is going into the intersection 60 miles per hour and the car is going away with 70 miles per hour, the cop is never going to catch up. If the car is going fast now, maybe the car can speed up. It has to speed up, otherwise it's not going to catch it. Yeah. For the reference, yeah, but for the reference, depending on whether you're going into the section or outside of the section, because if the cop, it will make sense, right? Because if the cop is pointing the other way, the distance is going to increase, right? It has to be the other way. Which makes sense.
It's pretty cool that they got numbers that actually make sense in the real world now.
But this models the world.
Yeah, no,
this
that's what I'm
is,
saying. It's
yeah.
cool. Like, how do these people make these problems? I think that's more interesting, making the problems rather than...
I'm going to make one for this class on next week, maybe Monday or Tuesday. I'm going to make one. But actually, you don't make them, you can measure them. Measure them. Because all of this stuff, see, if you're driving 60 miles per hour, that means that in 1 hour you're going to cover 60 miles. So if you're driving 60 miles per hour and you are going to DC that is 300 miles away, 60 divided into 300 is 5. It will take you 5 hours if you are driving exactly 60. Right? But you're not, right? You're driving much more because you end up being there in 3.5 hours, so you go figure out what the average speed of that, right? Which is why so we'll be talking about this stuff exactly, and yeah, it's cool. Anything else? We have 2 minutes left and then another 20 after. If not, book in the labs.
You still want one from 3.6?
Sure, why not?
What do you want, like the cost thing or the acceleration?
Anything.
Got it, boss? Smart, right? Hey, yeah, we gave up on 3.6. The equation is given, just take the and plug a number. There's a 3.6. Here, I'll closer to a 3.6. Take the derivative of a given equation, plug a number in. There you go. 3.6 over.
Only roll that simple.
Hey, it's calculus. What are you going to do? Lab time?
Yeah.
All right. All right, so then that's it for the review.